Hello, thanks for watching the second video in this series of lectures. This one is on conservation of energy, and the essential question is how do we keep track of energy moving around in a system in order to make energy transfers and transformations more efficient? So whenever you're approaching a problem from an energy perspective, the first thing that you really have to do is to think about it as a system and try to figure out how we're going to use this big idea of conservation of energy in closed systems to help us understand the energy state of that object. So let's take a pretty simple example. A ball starts at the top of the hill and then rolls down to the bottom. The first thing that you need to do is decide which objects should be inside my system, and also which two moments in time do I want to study. Two or more, of course. You could pick as many instances in time as you want because energy is going to be conserved at every time, but usually there's kind of a before and an after. In this case, I would probably say before rolling, and then near the bottom of the hill would be the two times that I'm interested in. As far as the objects that I want to include, in this case I'm going to need to include the ball, obviously, and you also need to include the hill because the hill is what's giving the ball its gravitational energy. So you should have the ball and the hill in both your before picture and your after picture. It's useful for those pictures to kind of show what's going on. So in this case, I have the ball at the top of a hill, and then I have the ball at the bottom of the hill. You can kind of picture that little asteroid thing as a planet, and the ball would roll down the bottom of the hill on that side of the planet. So after you've got your systems drawn and you've thought about the instance in time that you want to analyze, the next step is to figure out what kinds of energy the objects in your system have, roughly speaking how much they have, and also think about how you know that they have that kind of energy. So we've got our two systems again, before rolling and near the bottom of the hill. That ball before rolling really only has one kind of energy. It only has gravitational energy. It's got height, but it's not moving. Not much else is going on with that ball. So I would say it has a lot of gravitational energy. It's all the way at the very top of the hill. It's as high as it can possibly be. And that's the only kind of energy that it's got. Now, when the ball moves to my rolling state, my second system, and it's near the bottom of the hill, the energy situation has gotten a lot more complicated. For example, we still have a little bit of gravitational energy because I said near the bottom of the hill. So my system has to have some EG in it. It's going to be a small amount of EG because it has lost a lot of its height, but it does still have some. So what other kinds of energy does it have then? If it lost all that EG and it must have been transformed into something else, what did it turn into? Well, probably most of you guys are going to say EM. That ball is moving as it's rolling down the hill, and that's true. So we have some motion energy as well. I'm going to say a medium amount of motion energy just because there's a lot of other kinds of energy the ball could have. And the way we know it has motion energy is because it's moving. The third kind of energy that the ball has is rotational energy because the ball is rolling. Again, we're going to say it's got a medium amount of that rotational energy because we still have some other kinds of energy to come. Fourth kind of energy that it has gained as it rolls down the hill is thermal energy. Anytime an object rubs against another object, it generates heat. If you rub your two hands together right now, you'll notice that they'll heat up. So just by virtue of it rubbing against the earth and rubbing against the air molecules as it passes, that ball has actually heated up the hill and itself and gained thermal energy as it rolls. Again, I'm going to say it's got a medium amount because it looks like a pretty big rough hill that it rolled down. The last kind of energy I would probably think about is wave energy, which it has because it has made noise as it rolls down the hill. You could probably hear it. And that wave energy must also have been, coming from this gravitational energy that it started with because energy is conserved. So in my before system, we have one energy, and in the after system, we have smaller amounts of 5 different types of energy. So the last step in my analysis is going to be to make some energy transformation bar charts that show more quantitatively or more mathematically where that energy came from and where it's going. So again, I'm going to decide divide this into two parts before rolling, and then also a time later on near the bottom of the hill. And I'm going to make a bar chart that shows all the energy present in the system and roughly, in my guess, how much there is of each type. So what you can see here is that when we start, the only kind of energy we have was this gravitational energy. And since it's the only kind of energy, we've got 100% of gravitational energy. It's the only kind we have, okay? I also have this pink bar here, which is total energy. And since, again, there's only one kind of energy, it's going to be the same amount as it had gravitational energy. So 100% of the energy before it rolled was gravitational energy. Now let's move over here to my near bottom of the hill bar chart. I gave it a little tiny bit of gravitational energy again because it was near the bottom of the hill. It hasn't quite reached the bottom of the hill, so we still have a little bit of gravitational energy. I gave it just some sort of medium amounts of all the other kinds of energy, my motion energy there, and my rotational energy here, and my thermal energy here, and my wave energy here. The exact amounts were kind of just my opinion about what this was. Sometimes it's really clear that one of the types is going to be dominant, but in this case I think that it's pretty reasonable to think we've got small but non-zero amounts of all of those types. Of course, if you can add up all those values, I've got something like 5, 30, 20, 30, and 15. If you add all those up, you're going to end up with 100, which is the total amount of energy that I started with, because that's the big idea here. Energy is conserved. It might change from being a big hunk of gravitational when we start to a whole bunch of different types of energy near the bottom, but we still have maintained the same total amount of energy in your system. The last thing that's important that you realize, and you can really see it well in these transfer charts, is that some of those energies are kind of wasted, right? You might want to roll a ball down a hill to accomplish some purpose, to make it go fast, to use it to do some kind of work at the bottom of the hill. And so some of those energies are useful, like maybe the motion energy is very useful. Rotational energy can be useful sometimes too. But other kinds of energy are usually not useful, like the sound energy and the thermal energy in this case are just kind of byproducts of the fact that that ball rolled on the ground. And so whenever you have an energy transfer or a transformation, there is a loss of efficiency. We don't get all the energy that we put in out as far as useful energy goes. And so one of the reasons these bar charts is so useful is because as a scientist or an engineer, when you're trying to solve a problem, you're often trying to figure out how to make the best use of your energy. You're trying to maximize your energy. And in that process, one of the things you should think about is, how could I minimize these waste energies? So if I wanted that ball to roll faster down the hill, what could I do to make these two energies as small as possible so that the other energies that I really want could be bigger? So for example, maybe I could reduce the friction of the hill, make it slipperier, right? Build a slide on the hill, for example. I think you guys could all agree that if we had a slide on that hill, while we'd still have 100 joules of total energy at the end, we'd probably have a lot more of that motion energy and a lot more of rolling energy, and we'd probably have a lot less of these wasted thermal energies and probably less wasted sound energy as well. So one of the things I want you guys to get out of this bar chart is a sense of what are the kinds of energy we were intending to get, what are the byproducts, and maybe some thought about how we could increase the efficiency of our processes. So to summarize, please look back on your essential question: how do we keep track of energy moving around in the system in order to make energy transfers and transformations more efficient? And think about the tools that we've talked about in the last few slides to keep track of all that stuff. And I would recommend filling out the graphic organizer or working on the extension questions to help be prepared for the next class. Thank you.